Thank you for the kind introduction. Let me talk about our ongoing research. I'm Dániel Nagy, supervised by Zoltán Zimborás. I'm a PhD student at ELTE and also working at Wigner. So I will shortly motivate why we do this, then introduce shortly to reinforcement learning, proximal policy optimization, and quantum reinforcement learning with proximal policy optimization. And then I will talk about our approach of latent space QRL, and then I will show some numerical results. So we are in the era of noisy intermediate scale quantum devices. We already have around 100 or even more qubits, but these are very noisy. We are shortly approaching the regime of practical quantum advantages. There were already a couple quantum supremacy experiments which demonstrated some kind of quantum advantage on both superconducting architecture and photonic architectures. So in this NISQ era, some of the best candidates for potential quantum advantage are the simulation of chemistry, the variational optimization algorithms, and of course, quantum machine learning, which includes quantum reinforcement learning. And here we also have hybrid quantum classical solutions, which are enabled by high performance classical computers. So quantum reinforcement learning is a very new field with a lot of papers and research going into it, but it has some limitations because many of the reinforcement learning environments we want to solve have high dimensional observation spaces, like for example, visual data. And we would need a very large scale quantum computers if we would want to encode all the features into a quantum state. So a pretty straightforward solution is to extract some of the features using some kind of classical feature extraction method and use the latent features for quantum reinforcement learning. So let's briefly review what reinforcement learning is. In reinforcement learning, we have an agent that tries to navigate inside an environment by observing some states of the environment and performing some actions based on the observed states. And the environment gives some kind of reward for the agents, whether the action was good or bad in some sense. And the goal is mathematically to maximize the expectation of the time discounted rewards on the long term. Many of the agents here are implemented as classical neural networks, or in our case, quantum neural networks. There are very many methods for optimizing agents. Some of these methods have access to the model of the environment, some do not. We choose proximal policy optimization because it enables convergence in many environments, both discrete and continuous. So proximal policy optimization applies an actor and a critic, and both of them are neural networks, and both of them are optimized with the time difference error. The actor is also called policy in literature, and the critic receives the rewards and tries to estimate the temporal difference, which is used to optimize both actor and critic. So we want to find the best policy in a certain environment, actually the best parameters of a given policy. And proximal policy optimization essentially helps us to write down a single objective function that we can use in a gradient descent method. And the property of this objective is that it enables a pretty stable convergence of the agents. So how do we use quantum reinforcement PPO. Our approach is to keep every part of the system classical except the actor, which we implement as a parametric quantum circuit or quantum neural network. And we encode the observed states from the environment into the initial quantum state of the parametric quantum circuit. We apply a parametric unitary and then perform some measurements and compute the actions based on these measurements. So, as I mentioned, we want to use quantum reinforcement learning in latent space, and we have a pretty complex diagram which explains each part of the approach. First, we have an environment on top, which gives us some observable, but this observable is high dimensional. So we put the observable into an encoder and extract some kind of latent feature vector, which we use to encode it into a quantum state of the quantum policy. But this latent features vector is also fed into a decoder that tries to reconstruct the original feature vector, and we compute a reconstruction loss from the original observable and the reconstructed observable. And we also compute the PPO loss based on the action of the quantum policy. And crucially, we then combine these two losses into a single loss function, which includes both the PPO loss and the autoencoder reconstruction loss with some weight. And we train every part of the neural networks, both the quantum and the classical, with this combined loss. So let me show you some numerical experiments. We tested this approach in various configurations with 3 environments. 2 of them are very simple environments included in OpenAI Gym, and the last one, the maze we know, is a visual environment which much higher dimension. We also compared various sizes of autoencoders and various number of QNN layers, both qubit-based and photonic QNNs, and both cold starting approach and a pre-trained approach. So the most interesting environment we tested is this maze environment, which is a 48 by 48 grayscale image, and the goal is to navigate the gray box into a goal while avoiding collision with walls. And the agent starts at a random cell at every time. Now, of course, this is a very high dimensional feature. You cannot encode it directly into a quantum agent. However, we can use this latent feature approach. We test this environment with both quantum neural qubit-based quantum neural networks and photonic quantum neural networks. On the qubit-based version, we use a standard strongly entangling layer, and for the photonic one, we use a standard continuous variable QNN layer. We also apply data re-uploading, which means that we encode the data again and again at the beginning of every layer. So our results with the qubit-based approach were simulated with PennyLane simulator, also using TensorFlow to make it faster. And we compare different sizes of autoencoders with one QNN layer on the left, and we also have classical baseline with purple. And our results show that there is a little bit of trade-off between the autoencoder size and the number of QNN layers. For example, on the right, you can see that we chose the smallest autoencoder, and in this case, it requires more quantum layers for a better convergence. And we have very similar results in the photonic approach, which is simulated with the Picasso simulator software, which Zoltán talked about recently. Here we see a very similar trade-off between the autoencoder size and QNN layer counts, but we also see some signs that the quantum agent might be a little bit better in some cases. Now, let me mention that these curves are the smoothed averages of 8 agents, from which we dropped the worst performing 3 ones. So it's actually an average of 5 agents. And this is because reinforcement learning by nature is stochastic, and we want to verify that our method is good by running a number of agents in parallel with different random seeds. For the photonic simulations, we use GPUs because for the qubit version, it was slower on GPUs actually. So in conclusion, we demonstrated that this approach of training autoencoders and QNNs together enables the application of quantum reinforcement learning in high-dimensional feature spaces. And we also showed that joint training of classical AIs and QRL agents is necessary for the convergence. We see a little bit of trade-off between the number of QNN layers and the size of the autoencoder. And we see that in some cases, the quantum method can a little bit outperform the classical approach, but this needs further research to understand correctly. So for future, this is an ongoing research, and we expect to publish a manuscript soon. And further, we could tweak the method to include more quantum, like, for example, we can change the critic to be quantum as well. And we might try to find the best value for the C coefficient. So thank you very much for listening.
Nick? It was an excellent talk. So questions from the audience? Please. We have many times. So
really no other people who want to ask questions.
No, that's okay.
So very, very nice. Can you say a little bit more again? Maybe I missed it when you explained the different colors and the left-right plots. And are those all for, yes, for the maze experiments or?
Qubit-based or photonic-based?
We can start with the qubits, and then if we have time, we go to the photon. So for example, here, what's the difference between the left and right plot?
So in the left side, we fixed the number of QNN layers to 1.
Ah, okay.
And we try different convolutional autoencoders. And
but the convolutional autoencoders are the classical ones, the compression step.
Sorry.
The autoencoders are the classical ones. They are the compression steps.
The autoencoders are classical.
So they have an impact.
And we only use one QNN layer. And the smallest one is the V3 that has the worst performance. And the largest one is the V2, which actually has the best performance.
Okay.
As expected, actually. And on the right side, we fix the autoencoder to the smallest one. And we try different number of QNN layers. And also, as expected, if you have a very small autoencoder, you need more quantum layers. This proves that the quantum layers are actually doing something to help the learning, not just sitting there.
And the classical CNN is?
The classical CNN is just a baseline. It has a little bit more parameters than the quantum and the autoencoders together. So it does not actually prove that the quantum approach is better in every case. But for the photonic version, we saw that that it looks like sometimes it can be better.
Yes. No, but my question was whether the CNN replaces only the quantum, so you still run the autoencoder and then you run the CNN on the latent space as you do in the quantum, or you just use CNN and you skip and CNN.
So the CNN receives the high-dimensional picture.
Okay, right.
Okay. Zoli, please. Great talk. So my question is that, so when you run the photonic experiments, then what kind of parameters did you use, or how many number of modes did you use, what cutoff, and how much time did it take to like produce these graphs?
For these environments, the photonic simulations took a couple of days on GPUs to train. We used a cutoff dimension of 16 and 20. And the number of parameter is like, for example, a couple hundred. So here are the photonic simulation parameter counts.
Okay, thank you.
But of course, because of the high cutoff dimension, the actual Hilbert space is quite high, quite large dimension.
Yeah. Okay, thank you.
Maybe I have a silly question. If you could go back to the regard picture as which was discussed, just the one before the.
A little bit louder.
Yeah. Okay. Sorry. Maybe it's a silly question, but can you go back to the regard graphs? So my question is, if whatever it is, I'm not familiar with what is in the background, how you calculate this, but what I see just with the naked eye, that some of them has less fluctuation and the others are very straightforward. Is there any reason for this one? So what could be the issue that, for example, if I'm checking the let's say blue line is very much fluctuating in compared to the others? Is it just an artifact?
So what could be the problem because of this?
No, I think it's not a problem. It just can be. What is the reason behind? How can I understand that why some of the curves are so smooth or relatively smooth, and the others have big fluctuations in the episodes?
Yes. So because the blue line shows only one layer of QNN, so when you update a network which has a few parameters, then this update could be destructive. However, if you have many parameters, then each update is a smaller contribution.
Okay.
So, and
So
also
as far as
averages
go
of
more
many
deeper
agents.
network, you have less fluctuations and more.
Sorry.
So as far as you go for more structure, more larger structures, more parameters, then we smooth it out.
Yeah, generally, yes.
Okay. Further questions from the audience? Sorry, please.
So I assume that you have worked with exact gradients, but have you considered like sampling from the distribution and use stochastic gradients? So like
No,
you have an estimate of.
Right now we treat these qubits and qmods as if they were perfect, and we use homodyne measurement, which is calculated by Picasso, not sampled. And on the qubit setting, we use a computational basis measurement. So expectation values of Z operators.
Okay, thank you.
Because the maze has discrete actions, doesn't it? The maze example. Yes. So how do you deal with the case where you have continuous actions? Can you do that? And this, if your actions are continuous in a continuous space, how do you deal with it?
Yeah. So this is a discrete action.
Yes.
And we compute homodyne measurements and we get real numbers. And from those real numbers, we construct a categorical distribution and sample from that categorical distribution. So we actually, when we measure the probabilities of each action. Yeah.
Okay. Further questions or remarks? I cannot see. Yeah, sorry. No, yeah, already.
but you can also use particle number measurement, right? So if you want to have like a discrete output, then so have you tried using that instead of the? Okay.
We might try in the future.
Yeah. Sophia, if you have more questions. No. Okay, so then I cannot see any further things. So I really thank you for your talk. And I'm calling the next speaker, who is Urs Legeza. And Urs just arrived. Excellent. So Urs will speak about